Hello everyone, welcome back to Unite Coaching. In this video, we are going to see the first part of your syllabus, material and construction, in which the material that will be covered in this video is cement. So let's start with the video. Now the topics that we are going to discuss in this video are, see, first we will see the history of cement, then we will go with the definition, standard definition, what are the constituents of cement, then composition of cement, box compounds, their functions, then we will see the hydration process, then manufacturing processes of cement, then what are the various types of cements and where they are used, then properties of cement or various tests that we carry out on the cement, and at last we will discuss basic properties of cement ingredients. So this video gonna be a very long video, but I will cover each and every part of the cement related to the cement. Each and everything will be covered. That is, from exam point of view, this video is gonna be so important. So let's see them one by one. First, let's start with the history of cement. So the history of cement starts with John Smeaton. See, in 1755, John Smeaton, who was basically civil engineer by profession, he made very important contribution to the development of cement. And at the time of planning the construction of third Eddystone lighthouse, he introduced one cement. What he needed a hydraulic mortar that would set and develop strength in 12 hours period between successive tides. Means he made some calculations, and he concluded that for every 12 hours there is a wave which comes to the eddy house. So for that he needed a hydraulic mortar. So this is the first contribution made by a civil engineer, John Smeaton. Then James Parker developed a cement in 1780s, and it was one of the most famous cements in the history, and he patented it in 1796 as Roman cement. Then Joseph Aspdin took out a patent in 1824 in the UK for Portland cement. Now this is one of the most famous cements. Even nowadays you use this cement, Portland cement, or you hear this concept. So in which he used the mixture of lime, clay and water. Basically, what is Portland? It is a stone in UK, England. It is found in England. From that he made one cement, that is Portland cement, and he patented also that cement in 1824. And in 1908 Jules Bight patented a cement as calcium aluminate cement. And in today's era we have so many cements that we have instituted various civil engineers, various researchers, they have introduced so many cements. So nowadays we have many types of cements. So this was the history of cement. It started with John Smeaton in 1755. Then he needed a cement that would set and give the strength for 12-hour period, because there was a successive tides there. Then James Parker came. He introduced one cement as Roman cement. He patented that also in 1796. Then Joseph Aspdin came. He patented it in the 1824, as the name of cement was Portland cement, and it is one of the most famous cements nowadays also. And in 1908 Jules Bight patented one cement as calcium aluminate cement. Then let's see what exactly is the cement. See, cement is a mixture of calcareous, siliceous and argillaceous materials and other substances. Now what is calcareous materials? Calcareous materials means limestone, chalk, cement rock and marine shells. These will come under the category of calcareous materials. So cement is a mixture of first calcareous materials, then we have siliceous material. Now which is siliceous material? Simply silica and sandstone are the siliceous materials. Then argillaceous materials, as it is a mixture of calcareous, siliceous and argillaceous. So argillaceous materials are shale, clay, blast furnace slag and marl. So cement is mixture of all these elements or materials. and it is most commonly used cement. One of the most commonly used cement, as I told you in the previous slide, it is a Portland cement nowadays. And India ranks 5th in producing the cement, and China is the largest producer of cement in the world. So this is the definition or introduction, you can say, to the cement. Then let's see what are the constituents of cement. See, constituents of cement are lime, silica, alumina, iron oxide, magnesia, sulfur trioxide, and last soda plus potash. Now what about the percentages they have in the cement? See, lime has 63 average percentage, and if you want to have what is the range, general range, if you want to know, so the range of lime in the cement is 60 to 65%. Similarly, silica is 20% in the cement, or if you want range, it is 17 to 25%. Then alumina 6.3%, and its range is 3 to 8%. Then iron oxide 3.6, 0.5 to 6 is the range, and average percentage we take is as 3.6. Then we have magnesia, 2.4% is the average percentage, and if you want range, it is 0.5 to 4%. Then sulfur trioxide, it is in the range of 1 to 2%, generally average percentage taken as 1.5, and last soda plus potash. Now what about the functions? This is very important from exam point of view. They can ask you what is the function of lime in the cement, what is the function of silica in the cement. So function of lime, see, controls strength and soundness. What lime does in the cement, it controls the strength and soundness. Then if lime is decreased, or if you take the less quantity, strength and setting time increases. Remember this. If you decrease the lime percentage, then strength and setting time will increase. Then silica. Silica gives you again the cement strength it gives. Then if silica increases, it results in slow setting. You have to remember these functions, okay? They are important because they may ask what is the effect if silica is increased in the cement. Results in slow setting, results in fast setting, both, none, or whatever is the option. So you have to remember, if silica is increased, then it will result in slow setting. Then alumina, it is responsible for quick setting. If you want to set the cement quickly, then you can increase the percentage, but it is generally, it is in the range of 3 to 8%. And if alumina is in excess, then it lowers the strength. Remember this. Then iron oxide. Iron oxide, you may have heard that it gives color to the strength, but also helps in fusion of different ingredients. Then magnesia, it imparts color and hardness to the cement, and if magnesia is in excess, if more quantity of magnesia is in cement, it causes cracks in the mortar. So you can't add more magnesia while production of the cement. Then sulfur trioxide, it makes the cement unsound. Then soda plus potash, it causes efflorescences and crack. So these are the various functions of various constituents of cement. Now fly ash is also added as an admixture to improve the workability. You may have heard this because it increases the workability and it does not affect the strength. Okay, so fly ash is also added. Then gypsum is also added to increase the setting time. Now what is the percentage of fly ash? It is generally added as 1%, and gypsum is added 2 to 3%. So what is the function of fly ash? It improves the workability. What is the function of gypsum? It is added to increase the setting time. First, tricalcium aluminate is formed. You have to also remember the sequence. If question is asked like this, which is the first compound formed in the cement? So they will have, or they will give you 4 options. So tricalcium aluminate is the first compound that is formed. So formation number will be 1. That is what the sequence I have given here. First compound to be formed is tricalcium aluminate, C3A. Now What is the function? See, it is formed in 24 hours of addition of water. As I told you, it is the first to form, so it forms in 24 hours after the addition of water. Then maximum evaluation of heat of hydration gives or is given by tricalcium aluminate. And check setting time of the cement. It also gives the setting time of the cement. Then what about tetracalcium aluminoferrite? See, it is the second compound to be formed in the cement, and it is formed within 24 hours of addition of water. And high heat of hydration is generated in initial period because of this. Because of C4AF, high heat of hydration is generated in initial period of hydration process. We will see what is hydration process. I will explain you in the next slides what is hydration. But remember, this also forms within the 24 hours of addition of water. Then comes tricalcium silicate. See, it takes a week or within week it is formed. C3S. It has good cementing properties, then responsible for initial strength of cement, then it contributes about 50 to 60% of the strength. For example, the strength of cement is 20 Newton per mm square, cement or mortar, whatever it is. So for example, cement strength is 20 Newton per mm square. So out of that, 50 to 60% of strength is given by tricalcium silicate. Then content is increased for prefabricated concrete construction, cold weather concreting. See, if you want to have construction in cold weather concreting, you can increase this percentage of C3S. Or if you want to precast fabricated or prefabricated concrete construction, so in that case also you can increase the percentage of tricalcium silicate, because it gives you the initial high strength na. So in cold weather construction, what you will need? You will need high strength in the initial stages. In factories, what you will need? You will need high strength in the initial stages. Then comes the dicalcium silicate. See, it is the last compound that is formed during the hydration of cement, and it has a very low heat of hydration. That's why it is the last to form, and responsible for progressive later stress strength. For example, see, if you look at this compound C3A, C4AF and C3S, they are giving heat of hydration or they are generating the strength in the initial stages, but in the final stage or later stage, after so many days, after even years, which compound will be responsible to give the strength to the cement? It will be dicalcium silicate. So what are the uses in which case you can increase the dicalcium silicate percentage? Heavy constructions like dam, hydraulic structures, bridges. In short, those structures in which mass concreting is done, in that case you can increase the percentage of dicalcium silicate. Now we will see the hydration of cement. See, hydration is a chemical reaction between the constituents of cement and the water, in which the major compounds in cement form chemical bonds with water molecules and become hydrated. See, whenever water is added to the cement, what happens? There is liberation of heat. Heat is liberated. That is what I have written here. Now, this process is known as exothermic process. Remember this also. Now, what is exothermic process? That process in which heat is liberated. So, the moment you add the water to the cement, heat will be liberated, and that process will be exothermic process. So, this liberation of heat by the addition of water to the cement is known as hydration of cement. And there is also one concept, heat of hydration. What is heat of hydration? It is the quantity of heat generated, and it is measured in joules per gram. This is also very important. If question is asked like this, what is the unit of heat of hydration? So you can answer, heat of hydration is measured, or it is a quantity which is measured in joules per gram. Okay. Then heat of hydration is most influenced by the proportion of C3S, C3A in the cement. See, heat of hydration will be influenced by the following compounds. Options will be C3S, that is tricalcium silicate, C3S, C3A, tricalcium aluminate, both, none. So answer will be both. It is influenced by both, na. but it is also influenced by water cement ratio, means factors affecting heat of hydration. Water cement ratio, fineness, curing temperature, all these factors affect the heat of hydration. Then 23% of water by weight of cement is required for chemical reaction. See, if it is asked in the exam like this, what is the percentage of water required for complete hydration of cement? So answers will be confusing. So I will explain you three things. See, 23% of water by the weight of cement is required for chemical reaction between the cement and the water. Now this water is called as bound water, and it is only sufficient for the hydration, but gel pores will not be filled. This is very important. This 23% water is sufficient for the hydration, but still there will be some gel pores. So to fill those gel pores, what you will do, you will add extra 15% water, and that water will be called as gel water. So what is the total? 23 plus 15. So I can conclude that total 38% of water by the weight of cement is required for complete chemical reaction, as well as to occupy the spaces within the gel pores. So there will be no capillary cavities will be formed. So 23% water will be bound water, 15% water will be gel water, and bound water plus gel water will be the total percentage of water that will be required for complete hydration as well as for filling the gel pores.